Thank you. So, hi everybody. Welcome to the second lecture. So, I will start by a very, very short reminder of what we saw in the first lecture before attacking the exact solution for confined systems. So, first of all, last time we have seen that for bosons with delta interactions, we can replace the interactions by a cusp condition. This condition writes where we introduce the relative coordinate for each pair of particles, x equals xi minus xj, and the cusp condition reads that the derivative of the many-body wave function at contact between two particles on the left and on the right of the contact is related to the value of the interaction strength, G, times the value of the wave function in 0. And there is a factor m over h bar square at 0 distance. The second, so this is an important result which has helped us to build the exact solution in the homogeneous system by Bethe ansatz. The second thing that I wanted to remind you is what we understood exactly using the Bethe ansatz is that since we have interactions that are contact, we can write the many-body wave function in terms of plane waves, and we have just plane waves like free particles, and we have just to match the plane waves from one coordinate sector to another one. And let me remind you that coordinate sector means an ordering of the particles according to their permutation of their indices. So for example, x of p of 1 is smaller than x of p of 2, etc., smaller of x of p of n, where p is the permutation that brings the integers 1 to n to another sequence, p of 1 to p of n. Okay, so we have n factorial permutation, when the permutation group is Sn, so the sum over all the permutation belonging to the permutation group, times an amplitude AP, so this is the Bethe ansatz wave function, times the plane waves that are written in terms of all this permutation, sum over J, of some wave vectors K permuted in the index J times the spatial coordinate xj. And we have shown that the wave vectors k's, that are the rapidities, satisfy some coupled transcendental equation called the Bethe equations that are determined in terms of a set of quantum numbers ij and scattering phases that for this problem are cotangent of, so sum over L, KL minus Kj over C, and the C is a constant which is proportional to the interaction strength G. And we have also seen that for the ground state, the set of integers so first of all, if the number of particles is odd, then ij are integers. If the number of particles is even, then ij are half integers. And in general, for the ground state, it is a sequence of contiguous integers, minus n minus half over 2, etc., n minus 1/2. Yes?
Well, when last time you described the two mechanisms to excite the particle, you said that it was just to change one of the integer to one of the integer outside of these two bounds. But is it obvious that it will not change the dephasing, because the arctan will shift, and so won't all the other states also take a minor change of this global phase?
So I'm not sure I fully understood your question. So the procedure is, we fix the choice of the integers, and then we find the kj. And arctangent is defined always the same way within one of its, I don't know, minus pi to pi. Somehow, yes. And okay, and the other thing, the ground state energy, I didn't have the time to write it explicitly last time, is built explicitly in terms of this kj. So this is indeed, you see that the ground state is the one with this choice of integers, we get the lowest energy, and if you change the choice of the integers, you get other values of kj, which has a higher energy.
In fact, the question was, if you take ij and you change only one of ij to
yes.
an excitation,
Mm-hmm.
will it change all of the kj because you are changing one of the terms, or does it change only one kj?
If you fix the, they are all coupled, the kj. You see, only in the limit of infinite interaction, then each ij fixes a kj.
So changing the set of all ij changes
yes.
all the local momentum.
Yes. That's why the problem is difficult to solve in general. Okay, so for the excited states, I will come back later on for in the case of the Tonks-Girardot limit. So for the Bethe ansatz, I stop here. Let me just remind you then, it's all in terms of plane waves, and it's only valid for the homogeneous system. Okay, so then today's lecture is about the case instead of confined systems. So in the case of the presence of an external confinement, in general, we cannot solve the many-body problem exactly. It's not integrable for arbitrary interaction. The only case where it is solvable is for two particles. So for example, if you have two particles, a harmonic confinement, and the arbitrary interaction G, then this problem can be solved. I have no time to describe the exact steps of this solution, but if you, as all the two-body problems, in fact, can be solved explicitly, but I can tell you that a specific problem can be solved in terms of parabolic cylinder functions. Which are related to hypergeometric functions, and they are called d nu. And the result is that if you plot the relative wave function of two particles, I remind you x for me is x1 minus x2, and we had solved last time the problem of two particles when we derived the cusp condition by making separation of variables from center of mass and relative coordinate, right? And if I have an external potential, confining potential, harmonic, like that, the beauty of it is that it remains separable in a center of mass and relative coordinates. And so this allows us to write it as center of mass square plus x square. There is some factor there is 1/2 here and 2 here. No, vice versa, sorry, it's the opposite. And in this way, we can factor out the center of mass also for the trapped system, and we solve a problem for the relative coordinate, which is then solvable by properties of differential equations. So the solution for this relative coordinate is this function, which I will plot it. And because I find it's useful, the shape is like that. So in absence of interactions, the ground state is a Gaussian. But if you have interaction, there is a cusp at the 0 distance that becomes bigger and bigger as you increase the interaction strength. Okay, so in particular, notice that if the by looking at the cusp condition, for the interaction going to infinity, the cusp condition is satisfied with finite derivatives if we have that the wave function vanishes at contact.
Sorry, so the interaction enters in the parameter nu?
Yes, exactly. So if indeed the parameter nu, as you ask, is obtained by solving a transcendental equation. Maybe I can show you this afternoon if you're interested, which is like that. Sorry, the alpha is the mg over h bar square, and the harmonic oscillator length. You remember the harmonic oscillator length is square root of h bar over m omega 0. So this parameter, interaction parameter for the trapped case, is related to some transcendental equation for the parameter nu. That is the following. This gamma is the Euler gamma function. So we have one gamma of 1 minus 2 over 2, and then we have gamma of minus 2 half, nu half, and the parameter nu enters in the energy, which is h bar omega 0 nu plus 1/2. So you see that the choice of the, and also of course the value of the parameter nu define the parabolic cylindric function, which then changes shape by changing the nu. So actually this, then I cannot resist, I show you also the energy levels as a function of the interactions. Because you see, we can immediately see what happens at 0 and infinite interaction, because remember that the gamma of negative integers is infinity. So this, for example, to find the value of the value of nu at infinite interaction is enough to set that 1 minus nu over 2 is a negative integer. And to find the value of the energy level at 0 interaction, we have just to set that minus nu over 2 is an integer. In this case, the denominator is infinite, and it will give 0 on the other side. So in general, we find that okay, the parameter nu and then the epsilon nu as a function of the interaction strength G has this shape. It's for 0 interaction, it is 0. It grows, and then I have several branches, okay? Then I have another branch up there, and so on. And the value tends to the value 1 at infinite interaction, and this is 0. So this is useful because it shows, it gives an intuition of how is the shape of the wave function at arbitrary interactions. In the limit of infinite, okay, so in the limit of, yes, question?
So
These other branches, we do not, they are sort of some type of other metastable states, if you wish. So other type of states, yes, we do not explore them in the usual two-body problem. But they are also there. So somehow, if you make a specific imprinting on the system, they can be accessed.
So they are like excited states?
Yes, they are excited states.
So you were talking earlier about the ground state?
Yes. Yeah, so this is the ground state branch, indeed. Thank you, Jerome. And these other states can be created somehow. And let me also mention that when we go to infinite interaction, then we have that, so for G equal infinity, nu is 1. And in this case, the parabolic cylinder function tend to Hermite polynomials times a Gaussian. And this is actually nice, and because it shows that in this regime of infinite interaction, we have a free problem, problem of free particles in the same potential. This is the same that we found in the Bethe ansatz up there, where at infinite interaction we had the kj were just 2 pi over L times some multiples.
Just a question about this. What kind of boundary condition are you considering? Because you have a potential which is this
Harmonic.
harmonic potential. So what kind of boundary condition are you assuming on your function? Is it just open boundary condition with
It's also an excellent question. No, I am working on the whole interval minus infinity to infinity and in the continuum, and I impose that the wave function at plus or minus infinity vanishes. As when you solve the problem of a single particle in a harmonic oscillator. And the other condition that I impose, of course, is the cusp condition at x equals 0. So by imposing all these conditions, that's the way I arrive to this equation, which allows us to find the energy levels.
so the x that you say that the phi relative is just this function, and the other one you can have momentum for the big X, which is just the moment.
Yes,
Center of mass.
it could be, yes.
So EU is this plus a continuum of energy levels, which is the for this.
No, because also the center of mass is trapped.
Oh,
But you can write the energy levels for the center of mass is like the same as a single particle with twice the mass. And so you know the contribution of that part as well. And okay, so and when we notice in particular for n equal 1, we get the first Hermite polynomial. And in fact, we see that sorry, there is an absolute value here. We see that this resembles the solution for two fermions in the same potential, but the two fermions would have a relative wave function like that, while the bosons have the absolute value. They have this relative wave function. So free fermions, non-interacting fermions, would be this blue line, and the bosons, the red line. And by the way, this coincides with what we want. Recall that this is the relative coordinate. So when we exchange two fermions, the wave function changes sign. It becomes negative here. While when I exchange two bosons, the wave function has the same sign, and this is the case for the red curve. Okay. So this is just an appetizer, because then the same type of idea can be using, say, resemblance between bosonic and fermionic wave function is valid in general and is the basis of the exact solution. So now let's see if I can do at the same time. And this solution was, that I'm going to write now, was invented by Marvin Girardot 5 years before the Bethe-Ansatz. So it arrived first, and then so the Girardot solution (1960) states that the exact solution for any trapping potential Vx, I first of all solve a single particle problem in this potential. Called Z. And so I find H naught phi j equal epsilon j phi j. I create some single particle orbitals, and then I can write the exact solution in the same potential for bosons at infinite interactions in terms of a fermionic wave function times a mapping function that makes the fermionic wave function, which was antisymmetric under exchange of particles, it makes it symmetric. So A, the mapping function, is a product of sign functions, xj minus xl. And actually this, you know, maybe some of you know in second quantization, is a Jordan-Wigner factor. And this psi f is the fermionic wave function constructed as an antisymmetrizer that is a Slater determinant with these orbitals that we have here. And the indices j and k run from 1 to n. So this is the exact solution provided by Girardot. It's very interesting because it's valid for any external potential. And it's, of course, so it's limited at infinite interaction. I told you there is no, just I finish, there is no solution at intermediate interaction. Okay, tell me your question, sorry.
Sorry, I was just wondering, is the function A times psi equivalent to the Pfaffian function, or is it another kind of...
It is another. Pfaffian is more complicated. Is made with pairs. But this is just an antisymmetrizer of a single particle. But sort of resembles, yes, I agree. And, but okay, so that shows that, so for zero interaction, we can put all the bosons in the first energy level of this trap. For infinite interactions, we can just put one boson per each energy level. So it is the interactions are so strong that the wave function must vanish at contact, and this fermionic wave function exactly does what we want. And also note that in this regime there is no energy scale associated to the interactions, so the problem is quite universal. The only microscopic parameters that we have are those associated to the single particle problem. Okay, so this is very useful, but the work is not finished here because we want to be able to calculate observables, right? So far is as beautiful as the Bethe-Ansatz. The advantage of working in this regime is that we can push calculations almost analytically to very far. And so we can learn a lot about the properties of this limit of infinite interactions that is called Tonks-Girardot. So Girardot, you saw, is the person who found the solution, and Tonks is the person who identified this model of hard core particles, but was studying it in the classical regime. So let's say that Girardot has really given a great contribution in, so, yes?
Just to clarify, if we consider the setup of the beta ansatz with infinite delta potentials, we can still apply this.
Not in sorry, I deleted, not in the beta ansatz itself because it's plane waves, but I'm going to show you that you can recover the beta ansatz when you set the potential to 0 here. You can see that easily because if there is no external potential, then let's do it immediately. If Vx is equal to 0, I have no external potential, then the phi j are just the plane waves with some wave vectors that we fix by solving a non-interacting problem. And in this case, I recover the beta ansatz solution. And there is a small caveat when we have no potential and when we have periodic boundary conditions, then we have to pay a little bit of attention. I put the attention sign, because the sign function of xi minus xj, this sign function, the product over all I and j of the sign function, it is antiperiodic for even n. That is, for example, if you have two particles, if you plot the sign of x1 minus x2 as a function of x2 at fixed x1, it is, opposite x2, x1. So for x1 larger than x2 is plus 1. For x1 smaller than x2 is minus 1. And if you are working on a box of size L, and you see that it's antiperiodic, the value at L is minus the value at 0. Then I want, however, that the full many-body wave function is periodic, because I want that psi of xj plus L, the bosonic one, is psi of xj. I put a B just to remind that it is a bosonic one. So how do? I use then an antiperiodic fermionic wave function. So if I take a psi fermionic antiperiodic, and I take a sign function antiperiodic, the two together make a periodic bosonic wave function. And in this way, it is an elementary explanation of why the ij of the beta ansatz have to be different for n odd or n even. Okay? This is the, but this is the example of in absence of confinement. Now let us make a second example in the presence of the harmonic trap, so that I write the wave function explicitly, that you see how it looks like. So for a harmonic trap, then I take the first two orbitals, phi, so phi 0, up to normalization. I don't care of normalization for the moment. You know that there will be a prefactor, is e to the minus z square over 2 in harmonic oscillator units. And the phi 1 is z e to the minus z square over 2. And then if I take this construction here, just to show you that it's really a determinant, the many-body wave function, psi of x1, x2, the bosonic one, is equal to sine of x1 minus x2 times, well, 1 over square root of 2, it's the n factorial term there, times phi 0 of x1, phi 0 of x2, phi 1 of x1, phi 1 of x2. And by this vertical bar, I mean determinant. So that means phi 0 of x1, phi 1 of x2, minus phi 0 of x2, phi 1 of x1. So if you replace these choices here, you see that this is equal to the modulus of x1 minus x2 times the exponential of minus x1 square half minus x2 square half. Okay, so we constructed explicitly the solution, and it has explicitly a cusp in the relative wave function. And this can be done actually for arbitrary n, and I let you play with the van der Monde determinants to write the general expression corresponding to this for arbitrary n. I think we can stop here. Questions?
For the general case, then we will need psi naught, psi 1, etc.
Psi n.
Okay.
Yes. And use the nth, so the phi n will be related to the nth Hermitian polynomial. Okay, so I think we can stop here since, we started at 15. No, then I can continue a little bit. Sorry, I was thinking we start. Yes?
The term with that sign in front is another, is a permanent, is another mathematical object or not?
The permanent is a symmetrized product, right? So while this is first determinant, and then I take the absolute value. So no, I wouldn't say that it is a permanent. Okay, so then let's, once we know the wave function, let's see how we calculate observables. So we keep the wave function and body observable. Oh, okay. For example, sure.
Is there a Fox space description?
Yes, Fox space, I think so, you can, but you have always to, also in the Fox space, take care of all the anti-symmetrizations. So you must know how to do it. Actually, the Fox space description is useful when you do the finite temperature case. And yes, we will see how far I can detail, but if not, I can show you later separately. Okay, so observables. We start from, as we have seen in the previous course in ultra-cold atoms, for example, one observable that we can measure is the density profile. This density profile, which in second quantization is defined as the psi-Dagger operator, psi, I put the hat not to mix with the wave function, and which in first quantization is the expectation value of the density operator, which is defined as sum over j particles, delta of x minus xj. And this one is the wave function. How to calculate this? Well, I plug in it the Girardot solution for the wave function. So this is the integral in the x1 in the xn of the wave function psi star, the bosonic one of x1 xn times this operator, the sum of deltas. It goes to see at position x if I have a particle xj. And psi is the state x1 over xn. So now, bosonic as well. Now you see that, in fact, for this observable here, so which I can also write as sum, I take the sum out, it's an integral in the x. And then I use in the, let's index 1, the xn, say minus the coordinate j. Then I have psi star b of x1, blah, blah, blah. At position xj, I put x, j plus 1, xn. And the same for psi b. So it's a psi b square modulus. You see that the prefactor, the sign function or the mapping function does not enter in this final because the modulus square of the psi b is the same as the one of psi f. So in fact, this quantity here is the same as the one of a Fermi gas in the same potential. So exercise again, demonstrate that the density profile of a Fermi gas can be written in a simple way as the sum 1 to n of the orbitals phi j of x square. Okay, so this we call it a fermionic observable. And when you want to know whether you reached the Tonks-Girardot regime, and you see that the density profile is the same as the one of a Fermi gas, then you are done. You know that the system is in this strongly interacting regime. And this was one of the ways the experimentalists were using to, say, certify that they had reached the strongly interacting regime. And I can also take profit of this point to answer to a question that I had yesterday. So how do I know how good am I? Am I really at infinity interaction? If I want to know that, I can, for example, do a numerical calculation and calculate the n of x at finite g and compare it with our exact solution n of x. And then what you will see is that for g sufficiently large, they will resemble a lot. And actually we have tried. Well, it's really easy if you have whatever code like DMRG or anything, you can calculate the density distribution with DMRG. You see that the weak interaction is smooth and probably so more concentrated towards the center. And when you increase the interaction, it gets broader and larger. And at very strong interaction, you start to have some oscillations. I enhance them, let's say. But the density profile at very strong interaction, it has some wiggles on top that are associated, well, some people call them Friedel oscillations. We may discuss if it is really Friedel oscillation, because Friedel oscillations are near a wall, and here there is not really a wall. But anyhow, there are wiggles on top of the density profile. So this is the G equal infinity. Say this is the G equals 0. And at intermediate to large interaction, for the density profile, our exact solution is a very good description of the strongly interacting regime. Do you expect that it will be true for all the observables, or where there will be observable maybe where the infinite interaction calculation does not give exactly the same physics of the finite interaction? So I don't know if you have an intuition on your experience, or in any case, I will try to show you. I will highlight you the case where either we have exactly the same behavior, very continuous, or where we have something different at finite interactions. So
So we took a break.
If you want, we can make a break, yes.
Are there questions?
Here, in the expression you wrote at the bottom of the left bowl, you have phi b of x1, etc., x, xn.
Yes.
But since this phi b configuration is totally symmetric when exchanged into particles, well, could we just suddenly n pi was exactly the same thing?
Yes. You can write it like that, integral in dx2, dxn. So you can always permute the particle and say that x is the first place. And you can get a psi of x, x2, xn, square modulus. Perfect. That's true, and it's actually quite an advantage when you have to do that. That's what we actually do, in fact.
Other questions? So maybe just a short one. So you said that this is a way to confirm that experiments are the strongly repulsive regime, but in the early days they didn't have access to the density profile.
No, but they calculate, well, indirectly they were looking at the width of the density profile, not the full density profile, the average width. And the average width is also, you see from here, that the average width is smaller at weak interaction and larger at larger interactions.
Okay, so don't forget to think about the question of break.
Yes, and no, well, there are several questions, but one question is, can you think of some this is the difficult question. Can you think of some quantity where the G equal infinity case will be considerably different from finite G? But I will answer okay, later. And the other questions in general is to think about how to write the wave function for harmonic trap at arbitrary n.
Okay, so let's take a break.
Take a break and come back in 10 minutes. Test. Blah, blah. Okay, so welcome back. Now we are going to attack another. So here we saw an example of an observable which is the same as of a Fermi gas, but not all the observables are like that, because the mapping function plays a role every time that we have no local observables. For example, now let's look at the one-body density matrix. Let me remind you that this is the key quantity to study off-diagonal long-range order or quasi-off-diagonal long-range order, the coherence of a bosonic system. So it's really an important quantity for bosonic systems. And it's psi dagger operator x, psi of y. And we are going to compute it for the Tonks-Girardot gas. So first of all, let me write it in first quantization, because we work in first quantization. And I'm going to use the same trick as the n here. So it's actually, its general definition is n integral in the x2, the xn. And then I have the bosonic wave function, psi star of y, x2, xn, psi of x, x2, xn. And I let you as an exercise to demonstrate that the two are equivalent. So, and Now I plug onto this the Girardot wave function, and there you see that since here it's calculated in y and here it's calculated in x, the sine function will remain. And in fact, that's what's actually happening. I get n, the integral in the x2, the xn, and then the sine functions, some of them will disappear. Those, for example, sinus of x2 minus x3, I find here and I find there, so it will disappear. But when I have the sine of x2 minus y, or x2 minus x, this term will remain. So you see that in general, I get that I will get a product of terms j1 to n sine of x minus xj sine of y minus xj times. No, because it can happen for all the others as well. So for j equal to, yeah, sorry, yes, sure. No, I thought you were mentioning, sorry. Yes, j equal to, because x1 is not in the integral. And then here I have psi star f of y and all the other coordinates, psi fermionic of x and all the other coordinates. So now I think it's useful if I detail the step of the calculation, because it's, in principle, you see, it's a many-body integral. I have these sine functions, and I have these functions here, so it's still a bit complicated. But you see that I can expand these are Slater determinants, and I can play a little bit with the Slater determinants to arrive to something much simpler than the initial many-body integral. So let's see, so just stay with me. There are just a few steps. So first of all, you know the expansion of a Slater determinant in terms of the sum of all permutation, of antisymmetrizer, and so on. That is what I am going to use now. So here I have n. Here I have all the integrals to n. Here I have these products that will remain the same. X minus xj and y minus xj. And here I expand the determinants. So I get that, let me do in two steps. First of all, I write the determinants. So determinant of phi j of xk star, where x1 is equal to y, and the second determinant of the same form, phi m of xl, where x1 is equal to x. And then okay, and now I expand the determinants. And you see, the first coordinate is, in one case, is fixed to y, in the second is fixed to x, and is not integrated. So it's practical to expand the determinant by the first column, such that I get out all the terms which contain y and x and are not integrated. So in other words, for example, the first determinant is phi 1 of y, phi 1 star of y, then phi 1 of x2, etc., then phi 2 star of y, phi 2 star of x2, etc. The last one is phi n star of y, phi n star of x2, etc. And if I want to calculate this determinant, I write it by expanding along this column, and I get sum over j of minus 1 to the power j plus 1, and then phi star j of y. And here I get the remaining terms. That is a minor of a determinant where I take out the jth line. So let me see how it's useful to write it. Is the sum over all the permutation, the sign of the permutations belonging to n minus 1. And then I have the product over all the L to 2 to n phi star of P of L of XL. Okay? So this is the typical expansion of a determinant along its column. Now I use it twice in my expression there to get this general form for the one-body density matrix. Is the sum over two indices, I and j, that correspond to this first sum here. I have minus 1 of j plus 1 plus I plus 1, so these two ones are not important, and I get j plus y. And then I get these products of integrals. Now I can write it one by one. So, well, first of all, I have 1 over n minus 1 factorial that was coming from there and there. Then I get the sum over two types of permutation, p and p prime, the overall sign of the permutation, and then I have the product over k, let's use another symbol not to mix with I and j there, integral in the xk, and I have the function sine of x minus xk and y minus xk. And I had the product there, but I collected here with the product of the integrals. And then I have this phi star of p of k of xk, phi of p prime of k of xk. We are almost done, because now you recognize something. Times the orbitals that are outside phi star I of y, phi j of x. So we are almost done. The final expression is like that, sum over I and j going 1 to n, phi star I of y, a function aij, a matrix of functions, aij of yx times phi I of x. And this matrix here of indices I and j is written in terms of these, you see here, we have single particle integrals. We have, it's really useful because we have turned the initial problem of coupled many-body integrals onto the problem of where first I calculate a one-body integral on the argument x for each coordinate x, k separately, and then I build a rest of this function here. So all this here, and you recognize that this is determinant of the minor of a matrix. Okay, so aij, and we are done. Let me write it explicitly. So aij is minus 1 to the I plus j, and then can be written as simple as the determinant of these one-body integrals, integral in dt. Then I have these two signs. let's see if it is, well, it doesn't, sine of x minus t sine of y minus t times phi star k of t phi L of t. And in this determinant, I have to take k different from I and L different from J. So there are many other ways where it can be rewritten. For example, for example, as the determinant of another matrix times the transpose of the inverse of that matrix. So the most important is this quantity here that I call pKL. And this one can be also, so now you see that we can treat these two sine functions. You see that the product of the two is something that can be, for example, I have here x, here y. So the first, and this is t. So the first sine function does this. The second sine function does this. And when I have the two together, means that the overall it's, say, positive, negative, positive, you see? And then when we have, and this can be also rewritten as the integral everywhere minus twice the central part, okay? These are just the calculation steps. That shows that this P, KL, is, sorry, questions? No? This pKL is the integral from minus infinity to infinity of these orbitals, phi star k phi L minus 2 sine of y minus x, if I take y larger than x, and then it's the same in the other case, integral to x to y, phi star k phi L. And this first one, we know that we have chosen orthonormal basis of the single particle problem, so it's delta KL. Okay, so this is a very nice and useful form, because if you have to implement a calculation, you have just to calculate these integrals of given orbitals from x to y, and then you plug into the A and you plug into the rho, and you have the one-body density matrix of an arbitrary, of a Tonks-Girardot gas in arbitrary potential. So, so then now I will copy it here, and we can step and make some comments onto it. Because there are many things that we are going to learn from this. So then, for a Tonks-Girardot gas, the one-body density matrix is sum over I and j of phi star I of y, some function aij of yx, phi j of x. First of all, look, this is very different from the one of a free Fermi gas. For a non-interacting Fermi gas at 0 temperature, this is also 0 temperature, the one-body density matrix is diagonal, so it has this form, sum over I1 to n. Also here, I remind you the sum was going to 1 to n, is phi star I of y, phi I of x. And actually, we can very easily recover this one. Just come back here. Remember the sine function we inserted because we had bosons. If we want to do the same calculation for non-interacting fermions, we just take out this sign. That means that the pKL is going to be a delta. We are going to reconstruct the matrix Aij will be also a delta, And we are here to the final expression for the Fermi gas. So this is actually something that you can derive also with Green's function method, so it's very well known. This is my way to recalculate it, but of course it coincides with what was known before. Second comment, once we have this one, we can check the off-diagonal long-range order. You remember off-diagonal long-range order? Okay, was the fact that it should or not tend to a constant at large distance. But here we are in a trap, so we need to modify the off-diagonal long-range order criterion. And in the trap, what we need to check is that once we expand the one-body density matrix in natural orbitals, that is, you see in the coordinates y and x, this is a sort of a matrix seen as in a continuum. Imagine that I diagonalize it. That is, if I write is that sum of lambda j and then some orbitals, phi j star of y, phi j of x. Then if you have a Bose-Einstein condensate, it means that you have one orbital that is macroscopically occupied, and is phi j, it becomes the condensate wave function. If off-diagonal long-range order, in this case, implies that lambda 0, let's say the largest of these eigenvalues, is of the order of n. So if you now have an explicit expression for this, and this is a very difficult calculation, you can check that for the Tonks-Girardot gas instead, we have lambda 0 that scales like n to the power 1/2. And so this shows as another way to see that we do not have a Bose-Einstein condensate because the largest orbital is not occupied by the full particles, but only square root of it. Okay, so this is something that we learn on the one-body density matrix. And there is another thing that I would like you to learn from this study is the following. Yes?
Because we had this picture where in the Tonks-Girardot limit we have a Fermi gas where particles are different orbitals, but here we're saying that there is a macroscopic occupancy of some 5G.
Yes, because what we look now, this occupancy is like looking at the occupation in momentum space and not the occupation of the energy levels. And stay with me, in a few steps, I will make a full plot of the momentum distribution.
I think the confusion is because you haven't really defined the natural orbitals.
Yes, sorry. For me, the definition is, it's an operative definition. I did not write it, but we can do that. So the natural orbitals, to obtain them, you have to solve this equation. To diagonalize, that's what I meant by diagonalizing the matrix, but I have not written it. But thanks, Jerome, yes. So the natural orbitals satisfy this equation. If I want to calculate them, I have to see this as a matrix and this is as their eigenvectors. Thanks.
Okay, over the n I understand, but over the n1/2 I don't understand.
It's a very, very non-trivial. This calculation is done, for example, in the Forrester paper. So you need to exploit the properties of this one-body density. It's beyond the scope of this course. But there is something else I can show you, is other general features of this one-body density metric. This is really very difficult to get it.
Sorry, I don't immediately see why these lambdas are supposed to be related to the occupancy of some momentum space level. Is it obvious?
Not yet, but we can get onto it by noticing that the momentum distribution is the Fourier transform of the one-body density matrix. So it was not obvious, indeed, before having this definition. In this case, you can, if you plug in this expression, you see that this is sum over j, and then we have integral in the x of phi j of x e to the minus akx, and the same for y. So, and that, in other words, this is sum over j, lambda j, and this is the Fourier transform of these orbitals, modulus square. So you see that you get the momentum distribution in terms of these orbitals. And if you have only one orbital, the momentum distribution is this, the Fourier transform of this condensate wave function. But don't forget, because exactly we are going to study the momentum distribution by knowing the properties of the one-body density matrix. So maybe I keep it there. Yes?
Do we have any expectation of what one is looking like for different kind of traps? I mean, natural traps like harmonic traps or free particles. What do we expect from this?
Yes, I will try to tell you now all that we know in general. And also the trap plays a role, but only at large distances. At very short distances, we have some universal behavior that is independent on the shape of the trap, because you are going to probe distances that are very short, and the system does not know yet that it is inside the trap, or does not know much. So, exactly, let me tell you now what we know about the short distance properties of rho 1. Short distance means that meaning that we want to know to determine its behavior for x minus y going to 0. And for that, we need another way of writing the one-body density matrix, which again is a bit related of the function to the function p that I was calculating before. So let me show you just one step. How are we doing with time? So the one-body density matrix again was written in terms of the fermionic wave function, like that, the product in of the integral in the xi, and then we had these sign functions, x minus xi, y minus xi, and then we had the fermionic wave functions, y, xi, and x, xi, where all these are there. And now you can view this as, if we call this function f, you can view it as the product over I to n of, so this is the integral in the xi, and that is the same function that we saw before, 2 sines times something, so you will not be surprised to see that this is like the integral from minus infinity to infinity of f minus 2 sine of y minus x, the integral x to y of the same f. Okay, is exactly the same trick that we used before. So now, so that was f. Now this product, it looks like a binomial power series. So there, it looks like product is something like a plus b to power n, where a is this first part and b is this second part. And it can be actually made rigorous, but if we use this binomial expansion, you get that this is equal to n, and then we have a sum, j from 0 to n minus 1, and then the binomial coefficient, n minus 1 over j, and then we have a minus 2 to the power j sine of x minus y to the power j, and then I have some integrals. So for the jth term, I have, for example, j integrals of x to y, the x2 to j plus 1, and then the other integrals from minus infinity to infinity, from j plus 2 to n. And then here I have the function f, which is the product of these two fermionic wave functions. It is a very useful way to write the one-body density matrix for the following reason. Because you see, again, we have get rid of the mapping functions. They are just in front. And here, moreover, I have a quantity that those who know many body physics recognize that this is the reduced J-body density matrix of a Fermi gas, of the one-body density matrix. And to verify the following, the first non-trivial term is the J equal 1. In this case, look what happens. The rho 1 for J equal 1 has this form, sine of x minus y, or y minus x, integral from x to y of this rho 2 fermionic of x, x2, y, x2 in the x2. Okay, and now if you do for small x minus y, you can demonstrate that this has a singularity like x to the minus y to the power 3 times a function which depends only on the sum of x plus y, on the center of mass of this coordinate. So in this way, this is really non-trivial that we have a singularity, a cusp in the one-body density matrix. First of all, you see that it comes from the cusp in the wave function. And second, since it is singular at small distances, it will imply power law decay of the momentum distribution in Fourier transform, okay? Because there is a general property that when you calculate the Fourier transform of a function to the power alpha like that, its Fourier transform is 1 power k alpha plus 1. It is a general property of Fourier transform. So this study allows us to tell that at large k, and because of the contact interaction, we have that n of k at large k tends to 1 over k to the power 4. And actually, we also know the prefactor. It's called capital C, or Tan's contact. And this capital C is related to the integral of my function f there. So we see that contact interaction imply a universal behavior of the momentum distribution at large momenta, and this one is independent on the trapping potential. And for those of you who know field theory, the same result can be demonstrated by an operator product expansion. So this is detailed, for example, in a paper by Bartensberger. Essentially, it's we have the initial operator, psi dagger x plus y, and in general can be written as a series of some, y, as some coefficients that depend on the relative difference, and then some operators then depend of the center of mass. So little r is x minus y, and capital R is x plus y over 2. And these are local operators, depending on the fields, maybe on their derivatives. So we have that, in fact, with this method, people have demonstrated that the O3, that is the one which has power 3 in this, is some free factor proportional, let's say, to this psi dagger of R, psi dagger of R, psi over, psi over. I finish. Yes? Question? Not question? Okay. So you see that this quantity is up to a factor is related to the interaction part of the Hamiltonian, exactly at contact, at a zero distance. Okay, so, but with our, let's say, elementary methods, we have calculated the prefactor. So I have not made explicitly, but you have to do this expansion in this function that is known. And we have demonstrated a universal behavior at large momenta. This prefactor, called the Tanz contact, is a very important quantity. And it's for example, as you have seen that is related to this interaction energy, can be calculated by several other ways. For example, it can be calculated, so the contact is proportional to the interaction energy, and so, for example, can calculate it by ground state properties. Moreover, since the interaction energy can be related to the total energy, there is another relation that links the contact to the derivative of the energy with respect to the interaction strength. And is it valid up to infinite large K? Not really. It's valid until the contact interaction description is valid. If I go to the microscopic scale where the interactions are not anymore delta, that's where this description will break down. But for ultra-cold atoms, there is a broad regime of wave vectors where it is assured for a very good, to a very high precision. And
in the sense, does the C depends on the confining potential?
yes, you will see when you do the exercise and when you calculate the F, because the F, you can see already, it's built in terms of the orbitals phi j. So the value itself of C depends on the type of potential. And this is the large momentum part of the momentum distribution. Let me now tell you what we know for the smaller k. And this one does not come from our treatment, but we can steal the result of the Lattinger liquid theory that I announced to you last time. So remember the ρ1 of xy at large distances, now for x minus y going to infinity, behaves like 1 over x minus y to some exponent. 1 over 2 kappa the Lattinger parameter exponent. So if I do the Fourier transform of that, I get that n of k scales like 1 over k to powers 1 minus 1 over 2k. And so overall, I have this picture for the momentum distribution of an interacting Bose gas and the Tox-Girardeau gas in particular, this shape. we have seen at large k, it has 1 to the power k to the 4 tails. At a smaller k, where the Lattinger liquid theory is valid, I have another power law, 1 over k to the 1 minus 1 over 2k. Okay, and then for a finite system, this will be cut at a wave vector which is of the order of the inverse of the system size, and then, okay, so it will be finite at k equals 0. So by keeping piecewise information of various theory, we obtain that the momentum distribution of an interacting Bose gas has this shape. So it has quite an important peak at small wave vectors, and it has a very large, so a non-negligible tails at large wave vector. So while, let me remind you, for a Fermi gas, how is the momentum distribution? It's flat up to the k vector kf. So this is for a Fermi gas. And for a Bose-Einstein condensate, you know it, it's a peak at k equals 0. In principle, a delta peak proportional to the condensate density. So this is a BC. And if you have a BC with some interactions, you may have extra correction at finite k that is due to the so-called quantum depletion. So call it this a Bose-Einstein condensate in 3 dimensions. And this is the picture of a TG gas in 1 dimension. And this shows that although we have mapped onto a free Fermi gas, not all the properties are the same. We are really dealing with interacting bosons, and we can clearly see it from this observable. This is...
Can one study the modification to the temperature of this? Because, for example, LF, we know that it's gain like this, plus correction, which will introduce a broadening of the window around KF. Can we expect similar things in the Girardeau gas?
Yes, that is a beautiful question, and that is the work that we have done. And the most important, let me say 2 words. 1 word is about the method, and 1 word is about the result. First, about the method. At finite temperature, we can extend the Bose-Fermi mapping to arbitrary state. And so that means that we can write the state of the system at finite temperature. Let me show you how that works. Well, let's see from where I could start. Yes. So at finite temperature, if we want to write the state of the system, we do not write a wave function, but a density matrix. So this density matrix is not the reduced one-body density matrix. It's the density matrix of the whole system. Can be written as the sum over all the particle numbers, over all the energy levels for these fixed particle numbers, times a factor that is just the grand canonical weight, e to the minus beta e alpha minus mu n, and then all these states. And for each one of these states, you can map onto a Fermi gas. But then you have to deal with this sum, which is a huge sum. And to do that, you use the same trick as we did for 0 temperature that way. And so you can compute also the one-body density matrix and the momentum distribution of a thermal Tonks-Girardeau gas by doing the mapping here. And about the result, so this was the 1 word about the method. And about the result, what we find is that these tails here at finite temperature increase with interactions. So was quite surprising at the beginning, because usually temperature fades and destroys everything. But it is only true if first we set the limit g to infinity, and then we study as a function of temperature. If we stay at finite temperature, there will be a crossover interaction such that the temperature will win over interactions at some point. And of course, all this is when we are studying the thermodynamics of a 1D system, and if we take even higher temperature, we are getting out from the one-dimensional regime, and we will start to populate the other transverse states of the system, and will be then completely beyond this 1D model. So, let's see. Maybe, well, how many minutes do I have?
Well, I think you can have
10
10 more.
more, okay. So maybe in that case, I can start the dynamical properties if you don't have questions on the momentum distribution. This was really, say, the momentum distribution is really an important quantity for us, and I wanted questions on this part before we start the dynamics? Yes?
Are there models where you can see some sort of phase transition between a free-forming gas and a non-zero gas?
This is a beautiful question, and we have an expert here in the first row. You can think of anions that you can sort of put a twist in the wave function when you exchange two particles that interpolates between +1 and -1. And then you can solve, use similar techniques and advance on the properties of such a case.
So where does what parameter corresponds to the anionic study?
Is when you write psi of x1, x2, you write is e to the I some phase, psi of x2, x1. So you see that if you have a phi equals 0, it's bosonic, and phi equal pi is fermionic.
So, sorry, I meant in these plots.
How will the momentum distribution look like in the anionic case? Well, maybe you want to answer, Andrea?
So instead of picking around k equals 0, you move a little bit toward k fermi. When you vary this parameter, I think this is the more important qualitative effect.
Thanks. Okay, so let me sorry, I have not seen.
Just this is for G equal infinity.
Mhm.
How does this n of k is modified when you take for a given interaction, for example, no interaction, which is the model of most? How does the G, this diagram modify when G is going to be finite?
So when G is finite and non-zero, we still have the tails because we see that these tails are there because of the cusp condition. And we have a cusp at any finite interaction. So we will still have the tails. When we decrease the interactions, this Latinger parameter will change. It will become bigger. So we will change a little bit this slope if we plot in log scale. So overall, for a 1D Bose gas, this is sort of general for an interaction strength. However, if you go to the Bose-Einstein condensate case, then it will definitely be different because you will have a macroscopic occupation of the state at k equals 0 if you are in a homogeneous case. So this is one quantity that is continuous when you tend to limit interaction going to infinity. Right? Good. Other questions?
Well, maybe just one thing. So I think Andrea's question from earlier about the scaling of the largest eigenvalue of G1, I think you can see it from here, from the formula from 4.1 that you have long distances.
Yes, but this is, okay, we would have to do that properly in the trap. So there are some, yes, and you are an expert actually of that.
I think the exponent you can just read off directly from here. The
The 1/2 is here is related to the. Yeah, thanks. Yes, sorry, I forgot to.
In the homogeneous case.
Yeah. I forgot to mention that you also have a very beautiful result of extension of that in the harmonic trap.
Yeah, no, fine, but I mean, it's just the same exponent essentially.
Yeah, the scaling does not depend on the parabola.
Even though the first time it was derived, it was really a milestone in mathematical physics.
Yes.
But now it's a standard thing from mathematical physics.
Are we guaranteed that the Bettinger parametric K is always larger than the 1/2, so that we have no
One.
problem with the fact that it's a peak, because if K was too small, we would get the reverse slope and going down to 0. So
Now, for our model for the Lieb-Lininger gas, we can calculate the Latinger parameter using the Bethe-Ansatz solution, and we get that it is between plus infinity and 1. And in fact, its physical meaning is it is the ratio between the compressibility of the free Fermi gas and the one of the Bose gas. And so the Bose gas is sort of always more compressible than the corresponding Fermi gas, and that's why the Latinger parameter is always larger than 1. And for this model. Okay, well, maybe I just set the stage and then we continue tomorrow on that. So. The other advantage of studying the Tonks-Girardot regime is that you can solve exactly dynamical problems. And so we can do two types of dynamics. First of all, you can study the small oscillations. For example, you can perturb weakly the system and see how it reacts. This is in the realm of the linear response theory, and so to understand this regime, you need to calculate some correlation functions. For example, the density-density correlation function at two different space-time points. This is the one you need when you want to study the perturbation of the system when you, for example, apply a time-dependent potential, and then by studying its evolution, it's through this correlation function. So, and the other case where it's written in terms of simple correlation functions is when you take out one particle of the system or you add one particle of the system. In this case, the corresponding correlation